Exercise 6.1. Find the equation of the plane pi that passes through the points A, B, and C with the coordinates shown. So it says give your answer in the form r equals A plus lambda B plus mu C. We use bold letters to represent vectors, but when you write them, you can't really write in bold, so you can draw a little arrow above it. To show that it's a vector, whereas lambda and mu are arbitrary real numbers. So r is an arbitrary vector, a, b, and c are fixed vectors, lambda and mu are arbitrary real numbers. So by allowing lambda and mu to vary, we get the entire set of the vectors r, which go from the origin to an arbitrary point on the plane. So a good way to start might be to draw a picture. So this can be our plane. Here's the origin down here, O. And then we know that there's some vector from O to the plane. So let's make this the point A. Doesn't really matter which point you choose. But so that's our vector OA. And we know that this vector is equal to 1, -1, and 1 because of the coordinates of A. And then we have our 2 points B and C somewhere in the plane. So let's say B, and then C can be over here. Alright, and so then let's just, take the vectors B and C. So this, let me just label this as the point A. So now vectors B and C, vectors AB and AC. And then from here we can just do a few calculations. So the vector AB is the vector OB minus OA. So it's 2 minus 1 is 1. -4 minus -1 is -3. And then 3 minus 1 is 2. Okay, and then we just need the vector AC. So that is OC minus OA, so 0 minus 1 is -1. 1 minus -1 is 2. And -3 minus 1 is -4. And clearly these two vectors are not multiples of each other. So from here, let's just get the equation of our plane. So our arbitrary vector r is equal to the initial vector, the one that gets us onto the plane to begin with. Remember there's a x, y, and z axes here. So x, nope, not x. Well, I mean, you could make it x if you like, but I like to make the one sticking up z. So z, y, and x. So these are our axes, and we have our plane somewhere up here. Anyway, I'm off topic. Our initial vector is the vector 1, -1, 1. So 1, -1, 1 plus. And then, oops, we need an arbitrary multiple of this vector here. So lambda times 1, -3, 2 plus, and then the arbitrary multiple of this other vector, -1, 2, -4. Observe that the vector equation of the plane is not unique. In fact, there are infinitely many choices of vectors you can use to represent the plane. You just need any two vectors that are not parallel to each other but are both parallel to the plane, and you need any vector that goes from the origin to a point on the plane. So there are infinitely many choices of these three vectors here. However, when you allow your arbitrary real numbers lambda and mu to vary, lambda, mu vary, real numbers, then you will end up with the exact same set, infinite set of arbitrary vectors r that point from the origin to a point on the plane.